So on the screen here, I've got kind of a sequence of these integrals. And if we take a look here, this one on the left is what we call a definite integral. This is where we started with these. A definite integral is what? A number, a fixed piece of area. Okay, so a definite integral is simply a number. Now there's three ways you can do an area, a definite integral. You can do geometry, if it lends itself to that. You can approximate, if that's the best you can do. Or we have this very helpful thing called fundamental theorem part 2, big F of B minus big F of A. Of course, to do that, we need to know how to do an antiderivative, and therefore that's why our emphasis this next week or so on how to do antiderivatives. In this particular one, and you wouldn't have to draw a graph to solve it, but one option would be to draw a graph. And from 2 to 5, you would find that, oh, that just makes a trapezoid for this particular one. So we could actually do geometry on this one. Or we could do the fundamental theorem, which would be the antiderivative would be 1/2 x squared plus x, right bracket, 2 to 5. And then we could do 1/2 times 5 squared plus 5, f of b minus f of a, right? F of 5 minus f of 2. And then I'd have 1/2 times 2 squared plus 2. And this would be 25 halves plus 5. This would be 4 times a half is 2. 2 plus 2 is 4. What's that? 12.5 plus 5 is 17.5 minus 4. This would be 13.5. So it's just a number. Definite integral, just a number. That's how we could do that. All right, then we moved ahead to this idea of an area function. Now, what's different about this one? You've got x as the right endpoint. The right endpoint's going to change. So every time you go to a new right endpoint, the right endpoint's variable. Every time you go to a new right endpoint, you get a new area. It creates a function where x, the right endpoint, is the input, and the output is the area. It creates a function. A function has a formula. In this particular case, we learned that it would be the antiderivative. Of course, we had to do some things with notation. I had to change it to t's instead of x's. Same business, though. And we learned that we could do 1/2 x squared plus x plus c. And then how could we find the c? That initial condition of that 2 right there. We would know that big F of 2 would equal 0. Of course, we call this little f in here, so the whole thing is big F. This right here is big F. So we can plug a 2 in there. 1/2 times 2 squared plus 2 plus c equals 0. We get 4 plus c equals 0. We subtract 4. We get c equals -4. So we get 1/2 x squared plus x minus 4. Whole different animal. Here it was a definite piece of area, a number solution. Here it's an actual function, a specific function, because we can find the c because of that right there. Now what about this one? What's going to happen on this one? Vertical shift. Different c, right? This one, it's still 1/2 x squared plus x plus c. Notice I'm writing x, not t, right? Because we know it's the antiderivative, but x is the actual variable. And so now we know that big F of 3 would equal 0. And so we get 1/2 times 3 squared plus 3 plus c would have to equal 0. That's 9/2 plus 3. What's that? 4.5 plus 3, that'd be 7.5 plus c equals 0. We get c equals -7.5. So this would be 1/2 x squared plus x minus 7.5. Again, a specific function, the same as this function, just a different vertical shift. Now, a little side note to this, I noticed, I was really happy to see on the quiz, some of you doing a really good job with this part. I even noticed a few people, let me go to a different page, I also noticed a few people doing this, which is absolutely okay. I might have shown a few people this individually. I don't think I showed the whole class this necessarily. But I also saw some people applying fundamental theorem part 2 to a problem like this. Now, fundamental theorem part 2 is really set up to do definite integrals, but it can be applied here. You could take this and say, well, I would do this antiderivative. Notice I'm doing it with t's this time. Do my right bracket and do the 2 and the x. That is perfectly legal to do. Think of this here as your big F without a c, because whenever we do fundamental theorem part 2, we don't have to worry about the plus c because it subtracts out. And so then they just did big F of b minus big F of a. Stick an x in there, which again reiterates why you end up with x's in these problems and not t's. And then minus, and now put the 2 in there. And you get 1/2 2 squared plus 2. And you get 1/2 x squared plus x minus, and then this would be 2 plus 2, which is 4. And notice you get the same thing without having to think of that initial condition thing. You don't have to think of big F of 2 equals 0 and solve. You end up with the same thing. You end up subtracting a 2 plugged in, which if you go back to the previous page, is the same thing we had here. You've got the same antiderivative function with a 2 plugged in, that's a big F of 2, and you end up subtracting it over because you're solving for c. So it ends up being exactly the same thing. It's just kind of 2 different ways of approaching it. Okay? So either way, when you get these area functions, will work. I kind of like that fundamental theorem part 2 thing because it kind of matches with what we do over here. Okay? Either way, it means antiderivative. Okay, now what about this? What about if we didn't know the left endpoint either? Right? We don't know the right endpoint, it's moving. And we don't know the left endpoint. What would you have? 1/2 x squared plus x. You wouldn't know c, right? I mean, what happened when you had a 2 here or a 3 here? It allowed you to find c. Well, if you don't know the right endpoint, which means if you don't know the right endpoint, it means it's a function, not an actual piece of area. And if you don't know the left endpoint, then you don't know the c. And so you just end up with this. Well, then the question, I think this is where the notation kind of comes from. Well, if you don't know the right endpoint and you don't know the left endpoint, is there any reason to put anything there? Right? Is there any reason to even have the a and the x if they're both kind of unknowns? And I think that's kind of where this notation comes from, is let's just take the a and the x off of there, which allows us to not have to mess with having t's there. We can just have this. And we call that the indefinite. It's indefinite because it's not a fixed piece of area. We don't know what those left and right boundaries are. And so what we find is this is just a way of writing the antiderivative, the general solution antiderivative with a plus c. These would be specific antiderivatives. This would be the general antiderivative. So most problems in calculus that involve the integral are going to be either the red one on the left or the blue one on the right. It's either going to be a definite integral or it's going to be an indefinite integral. The definite integral is saying find this fixed piece of area, which we use fundamental theorem part 2 a lot of the time to do. The problem on the right is an indefinite integral just saying find the antiderivative of this function. Okay? So this little squiggly integral sign means do the antiderivative, and this dx means do it with respect to x. Now, we'll still get some of these problems, and hopefully we can do them, just like we had to do in our last quiz, but we're kind of past that. You know, there they are, this is what you do. Hopefully you can deal with it, but most problems are going to be of this type here. Okay, so let's move forward and get into some of your homework problems. So, starting with, if nobody cares, we'll kind of start with number 3 here and talk about some of the things that come up here. Now, what you will find with the gateway test on antiderivatives is there are certain aspects of it that are different than doing the derivative. All right, the derivative gateway test. Now, whether it's harder or easier is probably an individual thing. Some will find one harder, some will find one easier. Derivative, you had a set of rules. If it looked like this, you do this. Okay? Now, but there's a lot of rules. So you have a lot to memorize. But if it looked like this, you do this. All right? Now, where did we run into trouble? Not knowing the rules. Algebra. There's a lot of simplifying. Your original function might be pretty clean looking, but your derivative ended up pretty messy. You know, some people forgot that when they did the derivative inside, they forget to put parentheses around it, right? There are a lot of those kind of things you can do wrong. Well, those aren't the same kind of things that go wrong on antiderivative. Antiderivative is more subtle. Antiderivative is more techniques, not rules. An antiderivative could look, one function that you need to do the antiderivative, you use one technique. If you change it just a teeny bit to where it almost looks exactly the same, you do a different technique. But the algebra won't be as big of an issue. So if that was a problem with you, the algebra, the simplifying that stuff, you're probably going to like antiderivatives a little bit. It doesn't seem to be as big a deal. Antiderivatives tend to go from messy at the beginning to a little cleaner looking at the end. Okay? But the thing you will really have to work on over the next week is identifying, I don't want to say when it looks like this, do this, but there's a certain amount of that. Identifying what technique to use, in what situations, and being able, here's where the practice comes in. I know I say this all the time, that you got to practice, got to practice, got to practice. But the reason for the practice on antiderivatives is because you run into kind of roadblocks, and you've got to know how to handle those. And to avoid the roadblocks, you've got to be able to see ahead. You've got to be able to look ahead a few steps. And you really only can do that through practice. That's really the only good way to be able to see ahead. All right? So, a lot of what I talk about today is going to be identifying some of those different roadblocks, some of those different things you want to be looking for. Okay, and then give you some time to practice. All right, this one is as easy and straightforward as it gets with U substitution. They tell you to let U equal sine x. Of course, after these problems, you're not going to be told that anymore. You've got to come up with it yourself. So one of the things I'll be talking to you a lot the next several days is how do you pick U? What do you pick for your U? The one thing I told you on Thursday was what? Remember? What's inside. The first thing you look for is what's on the inside. Okay, that's a typical first place to look for a U substitution. The next step, and I'll write it one more time. I told you on Friday I wouldn't do this anymore, or on Thursday, but what the heck. The next step is to do the derivative with respect to x. That's du dx. Now you might say u prime, but we want to write du dx. Why? Well, because we're doing antiderivatives, we're doing integrals, and they got dx's in them and du's in them. So we want those in there. So what's a derivative of sine x? Cosine x. Now we said we would do what with that? We would move the dx over to the other side. Now we do that every single time, so we're just going to start skipping that step right there. Something this important deserves a new one. All right, so we will skip this step, and we'll go right to this. So just think of the du as derivative of u. And that when you do the derivative, you tack on the dx. Why is the dx over there? Well, it came from this step that we're skipping now. It got moved over that one. All right, now the substitution. Now the name substitution comes from just that. We're substituting. Think of it like a basketball team. You got 5 players out on the court, the starters. Those are the x's, right? You're going to make a substitution. Now, when you substitute, you have to account for all 5 players. If you only want to substitute in 3, that's fine, but 2 have to stay there. Okay? So you substitute 3, 3 have to come out, you still have to end up with 5. Okay? Well, the analogy would work this way. I would look at this right here and say I could substitute that out. Now, the e is actually going to stay there, right? I'm not going to take the e out of there. The e is going to stay in the game. But what's going to come in place of sine x? U is equal to sine x. Okay? Also, and I'm looking here, I'm looking at what I got on the bench. I love this analogy. Looking at what I got on the bench over here, and I see I can take out cosine x dx, because the starters are screwing up. I mean, they're just not getting the job done. So we got to get the u's in there. So we got cosine x dx, and that could be replaced with du. Now I don't know why I wrote that time sign there. We usually don't write that. We don't want to write that. Okay? So there we go. Now, the key thing about it is I've accounted for everybody that was in the game. I've got the same number of players out there now. Okay? You've got to account. Now, I know you guys are going to be like every other class I've had for 15 years, and you're not going to want to circle things like I do. Okay? And you know, you're going to, and 85% of the time that'll work fine. But every so often, you may not account for something, and you're going to run into trouble. So whatever, it's up to you. But all right, so now I got that. Now I forgot to mention page 333, and there's something I want to talk about there when we get a chance here in a second when we get to a problem like that. But okay, on page 333, there's a list of basic integrals that you just have to know. All right, you just have to know those antiderivatives. And to be honest, if you know those, then the whole goal of every technique we learn the rest of this week is to turn the integral we start with into an integral that looks like page 333. Okay? That's the goal. All right, well this looks like one of them on page 333. It's an easy one. Antiderivative of e to the u is what? E to the u plus c. Now the question was asked last Thursday, and it's a fair question. What happened to the du and what happened to the integral symbol? And I think that the explanation I gave to you that time was this. If I ask you to do this, the derivative of x squared with respect to x, you would write what? 2x. What happened to the dx? I mean, you know, and I don't remember anybody asking me that question, but for some reason it comes up about every year. For some reason, it seems like something should happen to that. Here, it was telling you what to do. The d said do the derivative. The dx said with respect to x. This was saying do the derivative with respect to x. We did it. That's our answer. Same thing here. This integral symbol right here is telling you do the antiderivative. This is telling you to do it with respect to u. So we've done it. Those two go away now because they were instructions basically telling us what to do. We did it, and they're not needed anymore. Last thing then, we put the sine x back in, and we get that is our antiderivative. Now don't forget, now you can use your calculator to check them, and that's fine. Okay, see if you're getting it right. It's a good idea. So you can just type this in. But remember what an antiderivative is. It doesn't hurt to just take a quick peek and do this in your head. If I was going to do the derivative of e to the sine x, I would get e to the sine x times the derivative inside, which would be cosine x kicked out. Sure enough, there it was. It feels like this should be a hard thing to do with an antiderivative. If you look at it, you see e to the sine x, cosine x, it's like a product rule, or it's messy, what's going on? Actually, it's a good thing it was messy. It's a good thing the cosine was there. Look at the answer, how much neater and simpler it looks. You see what I'm saying? People tend to think that this would be an easier antiderivative to do than that one. It turns out not. It turns out this doesn't even have an antiderivative. Get your calculators out for a second. I want you to type this one in, this original one. Type in this original integral that we had. I think in the template there's one that doesn't have the a and the b on it that you can use when you're doing one of these. So type in that original one we had, and what do you get? E to the sine x? Right? It doesn't put the plus c. You have to do that yourself. Okay? Now try this one. Now try this one. Integral of e to the sine x dx. It just spits the same thing right back at you. It's saying, hey, there isn't one. At least that it can find. Now the calculator's not foolproof, but for the most part, the ones we do, it'll be. So there isn't one. And now that wasn't true with derivatives. Derivatives, we can handle anything. We had a rule for everything. Okay? Everything had a derivative. But for antiderivatives, it doesn't work that way, because think about what would have to happen. You have to find some function that when you do its derivative, it gives you e to the sine x. There isn't one. There is no function that when you do its derivative, it'll come out e to the sine x. So it has no antiderivative. All right. Another thing. Another thing I want to mention before we do another one is this natural log thing on page 333. If you do the derivative of natural log x, you get what? 1 over x. However, on page 333 it says if you do the antiderivative of 1 over x, you get what? Why? Why does it do that? Remember what you know about the, well, hopefully know. What's a graph of natural log x look like? What's its domain? All positives, right? Greater than 0. Whenever you deal with a function in math, whenever you're dealing with a problem and you're given a function, it has a natural domain. So any problem we do here that deals with natural log, it has to do with what you start with. If we start with natural log of x, we know in this problem x has to be positive. So therefore, its slopes will always be positive. Now, if you look at the graph of 1 over x, however, here's the graph of 1 over x. Is that the right f prime graph for this f graph? Well, right here, the slopes are positive and big. Sure enough, the y values here are positive and big. The slopes are positive and getting less positive, positive and getting less positive, right? That seems to match. What about this? Shouldn't be there, right? Shouldn't be there. The f prime graph, in this case, should just be one branch of the 1 over x graph. Now, why would we know that? Well, because we know in this problem, natural log x has to be positive, so therefore, in my 1 over x graph, I can only use x being positive. Now, I didn't have to write anything special, but we just know that's the domain for that problem. Now, let's reverse that. Now we're starting with little f being 1 over x, which is this graph. And we're wanting to do its antiderivative. What's the domain of 1 over x? What's the domain of 1 over x? Everything but 0. Can it be negative? So in this problem, x can be negative, right? So what would happen here if I didn't have the bars? That'd be bad. I'd be trying to put a negative into natural log, and we can't do that. So what we do is we put the bars here to make sure that we don't try to put a negative into natural log. Here would be the big f graph then. You would not only have this, because that would be the slopes, little f, but you also have this over here. That would be natural log with the bars around it. Because this has negative slopes getting more negative, and this branch would be negative and getting more negative, and so there'd be a match. So there's a difference depending on which one we start with. That's why the bars are there. You have to have them. Now there will be some problems where it turns out you wouldn't have to put them in if you don't want to, because they're not necessary, and you'll see that as we go. But it's never wrong to put them in, so a lot of you will just probably put them in to be safe. Okay? All right. Number 5. Integral arctangent x over 1 plus x squared, okay, dx. I'd write these down, guys. Chase, I think I'd be writing these down. Okay, we're talking about a lot of practice, right? You need a lot of practice for these. I think writing them down and follow along, I think it's a good idea. Now, maybe you got them already. Maybe you got them. I mean, that's fine. If this seemed easy to you on the homework, that's great. Don't worry, we'll get on to some tougher ones here, not too very long here yet today. Again, if this was derivative, this would look tough. I mean, it looked like a quotient rule, it'd be a mess, right? Well, it turns out that they tell you to let u equal arctangent x. Now, that doesn't fit what I told you earlier, that you let u be the inside, right? That's no inside. Well, sometimes you don't have an inside. So the second idea about what to let u equal is something so that when you do the du, it happens to also be setting there. Now, the last problem we did, both ideas worked. Let u be the inside, which was sine x, but also the du was cosine x, which happened to be setting right there. So this is another one that's about as easy as it gets with u substitution. Okay, it might not be quite as easy to see what to let u equal, but once you start getting the hang of it, you would look at this and say, man, this is an easy one. Because what's the derivative of arctangent? And a dx. Well, you start doing your substitution on this one, and again, it's pretty simple. We're going to take that one out and replace it with u. And this part is simply the du. I mean, this is 1 over 1 plus x squared dx. I usually circle it like that, but all right. I mean, that's the du. I mean, so that, again, as substitutions go, it doesn't get much easier than that. And how do you do that antiderivative? It's a power rule. 1/2 u squared plus c. You stick the u back in, 1/2 arctangent x squared plus c. And it never hurts to just do a quick little derivative of that just to see if it fits. The derivative of this, you do the outside first, which would bring a 2 down in front, cancel the 1/2. You'd leave the arctangent alone to the first, so you'd have an arctangent times the derivative inside, which is 1 over 1 plus x squared. So you'd have arctangent times 1 over 1 plus x squared, which is exactly what that is right there. Okay? But could you have come up with that? I mean, just looking at it? You know, but this technique makes it really pretty easy. All right. Number 7. So a lot of the ones we do here are about, hey, look what happens on this one. Look what happens on this one. You know, and then you'll practice them, and you'll come back, I got a question on this one. Oh, that's another situation that you got to look out for. And not, you know, and there's just a lot of those. The more practice you do, the more adept you'll be at seeing them. I really think this is kind of like traveling along, there's forks in the road. And you got to decide which way to go. Now, if you're experienced at driving and you've went those routes before, you know which route to take. Okay? Now, sometimes if you don't know where to go, you're going to take a wrong turn. Now, that wrong turn may eventually get you there, but it'll be the long way. I got all kinds of analogies today. I don't know what's so special about today. You may eventually get there, but it'll just take longer. Or you might hit a dead end and you have to back up. You know, some of you, you're going to come to me and you're going to say, hey, on this one, what should I let u equal? And I'm going to say, well, what do you think? They say, well, how about this? And I'll say, try it. You got to go down the wrong road a few times to learn what could happen. Give you an example from my algebra class. Okay? In my algebra class, if I gave you this problem, now you guys who've been down this road many times would know to do what? Derivative. You would do what? Subtract 3x from both sides, right? Because you know that get x's on one side, numbers on the other side, then you can divide and you'd have it real easy. In my algebra class, there's a lot of them that feel most comfortable if the x is always on the left side, right? They like x equals. So they would subtract 5x from both sides. Now you know subtracting 5x from both sides, what happens? Well, you get a negative on your x, number one, which can run into all kinds of issues, especially with that class. They run into. But isn't it another step? It adds an extra step because now you're going to subtract 5x and you're going to have to subtract the 2 over to balance out your sides, right? Now, you can still get there, just a longer road to take. Well, you're going to learn as you go through these which are some of the shortcuts. You know, hey, it looks like this, I could do this, but you know, if I went this way, it might be a little shorter. Okay? All right, so again, they're nice to us here. They tell us to let u equal 1 over x, which of course we know that's x to the negative 1. I think of it that way because I know next step is to do du. Du is what? A lot of people would have fallen right there, just so you know. All right, so what do we get? Negative 1 x to the negative second dx. Now this one's just a little trickier in a sense. It's a little bit of algebra to do. A little bit of algebra that you have to do to make the substitution look good. It's not quite as nice looking as this one. So when I come over here to substitute, of course the top thing there, that's e to the u. Okay? This part I can kind of see here, except it's got a negative. It's okay to multiply that negative over to the other side, since it's a constant. And I'm going to write the x to the negative 2 as 1 over x squared. Okay? Now maybe you could have done that without looking at that, okay, and rewriting it just to see it. But now it's pretty easy to see that 1 over x squared dx is the same as a negative du. So when I substitute that in, I'll put the negative out here because it's a constant. And the du always goes on the far right end. And now this looks a lot like the one we did earlier, number 3. Antiderivative of that is e to the u. The negative comes along for the ride. Put the x back in. And we got our answer on that. Okay? Now, number 9. E to the x, 1 plus e to the 2x dx. Now this one's probably the toughest one of all. Imagine if they had not told you what to let u equal. Okay? Now, they didn't. They gave it to you. They told you let u equal e to the x. So the du is pretty easy. E to the x dx. But what's hard on this one, I don't know about hard, but what's trickier on this one is the substitution. There are some mistakes you can make in the substitution here. All right? By the way, when I make my new integral, notice I always rewrite the integral symbol because I have not done the antiderivative yet. So I need that integral symbol still there. All right? Now, I helped a few people on this one, and every one of the people I helped made the same mistake. Easy to see why. They took this and replaced it with the u. That sound familiar? Did you do that? It's going to turn out that this will be the long road, but you can still get there. But I want to show it to you because some of you are going to go the long road. You got to see some of the things you can do when you get there. So then, here was a thing I saw from a couple people I helped. So they let u be that. And then they went to sub out this. Now, one thing to keep in mind, and here's some of the algebra that's good, is when you see e to the 2x, that's the same as what? E to the x squared. It's nice if you notice that. Because number one, that gives you an inside thing, okay, which can be helpful to find. And power on a power, you multiply. So e to the 2x is the same as e to the x quantity squared. So by knowing that, what's the bottom now? 1 plus u squared. Right? E to the x squared. Now, these particular people I was helping on this one stopped right there and we're trying to do the antiderivative now. Now, since I've been circling them, it's pretty easy for you guys to see what am I missing? The dx, right? It's like I haven't substituted out the dx. I've put these people in, but I haven't substituted out the dx. Okay? And I have to, because I can't have x's and u's mixed up there. And so when I pointed this out to one person, they did this. They said, oh, I said, well, what about the du? They had it written just like this. I said, what about the du? They said, oh, okay. And they put the du. Well, that'd be like putting somebody in a game and not taking somebody out, right? Now I got 6 players on the floor. Can't do that. Okay? And the problem is, look at this. This looks like nothing on page 333, right? There's nothing here that this looks like that you can do an antiderivative of. All right. So, let's get rid of that du. So what could I do? How could I get the dx substituted out?
Can you rearrange the du equation?
I can. We talked about how we can divide a negative over here. You could divide an e to the x over here. Now, normally you don't want to do that. Normally you don't want to mix up the e's and the u's. But it turns out, and you guys know how I feel about dividing, I would write that 1 over e to the x du like that. But it turns out that 1 over e to the x is what? That's 1 over u. Right? So that way now I'm not mixing up the x's and the u's. Now again, this is the long road, but we're going to get there. So now I can sub out the dx with a 1 over u, and I can't put that on the outside because it's not a constant. 1 over u du. Well, what happens? The u's cancel, and what am I left with? Arctangent of u plus c, which would be arctangent of e to the x plus c. Now I'm going to show you how we should have done it if we wanted to do the shorter one. Okay? What we should have done is let u equal e to the x du, how's that come? That work? Okay. E to the x dx. Okay? And now, instead, we should have noticed that right there. We should have noticed that e to the x dx is sitting there, and that is du. And that leaves me with 1 over 1 plus u squared when I sub out this bottom. Right? And now I'm right into arctangent right away, and I don't have to do any of that other messing around. Okay? But it was pretty easy to make that mistake on number 9. All right. I want to get into a couple other things that can throw you off. So I want to do number 29 on page 341. Now again, I would write this as, I would not write that dx on top. Oops, that's supposed to be 1 minus, isn't it? Okay, doesn't seem too bad. This is number 29 in your book. And as you notice, you do not know what to let u equal. Now some of you might be able to just look at this one and tell. Can anybody just tell this antiderivative? At least get us close in the ballpark of what it is, maybe not exactly. Remember in section 5.3 we had a scenario where we had a 1 over x plus 3 and we were doing the integral of that? There's a definite integral problem. What was the antiderivative of 1 over x plus 3? That was a natural log one. This is going to be a natural log. This is going to be a natural log. Now, one of the things that you guys will do, you might not think this right now, but you will get so used to seeing natural log ones because we see a lot of fractions in our integrals, and you'll see a lot of 1 over something and you'll think it's natural log. Be careful. 1 over x dx is natural log. But 1 over x squared, or 1 over x to the 1/2, or 1 over x cubed, or anything other than power 1, what rule do you use for those? That's power rule, right? You can't do power rule on x to the -1 because you raise it up 1 and divide, you end up dividing by 0. That's no good. But if you have x to the -2, that's a power rule. This is x to the -2, so you raise that up 1, that'd be x to the -1 divided by -1 plus c. So you gotta be careful not to overuse natural log. only when you've got 1 over something to the first power, and that's what we have here. So, what are we going to let u equal? One minus 2x. Now, that's the third idea about what to let u equal. First idea was the inside of something. Second idea was kind of something that is there. It might not be on the inside, but if you let u be that, the du will also be sitting right there. We did that with arctangent. We let u equal arctangent. The 1 over 1 plus x squared was right there. Okay? The third idea is let it be the whole bottom, or a big part of the bottom, or the inside. Of course, that goes back to idea number 1. But if you let u be the bottom, you'll end up with a 1 over u, which is natural log. Okay? Now, what's a du? Negative 2 dx. Okay? Now, I see no negative 2 in there, so what are we going to do with that? We're going to move it to the other side. So I said when I got in this problem that these are some other complicating factors we can sometimes get into. Okay? Well, the complicating factor sometimes is a constant that's in there that isn't in the original problem. Well, don't worry about those constants because those can always be moved over. Okay, so I would move it over and divide it as a negative 1/2. Now the substitution is pretty easy. This whole thing subs out as 1 over u, and the dx subs out as a negative 1/2, right, with the du out in front. Jake, Ryan, how you doing? We're not going to do much more with calculators, so you guys don't have to sit really, really close to each other. I mean, you can. I notice you kind of do, right? Yeah, I noticed that. You guys got a nice conversation going back there too, but you might want to listen to this. All right. So anyway, negative 1/2 ln u with bars around it. Don't forget about the bars. Okay? And then you put the other stuff back in. Okay? And I forgot the natural log. Don't do that. Okay? Negative 1/2 natural log 1 minus 2x. Now, as a check on your derivative, you know, the negative 1/2 would just sit there. You do 1 over the 1 minus 2x. The bars really wouldn't affect anything when you do the derivative, right? You just do negative 1/2, 1 over 1 minus 2x, and then you'd have to kick out a negative 2. Well, that negative 2 would cancel the negative 1/2, and sure enough, you'd end up right back where you were there. So let u be the bottom can be a good thing to do. Okay, let's try number 10. Number 10 gets into another thing that can be an issue. And trust me, there's many more things that could be an issue, but we'll do this one and then do one more example of a definite integral and how that changes things, and then give you some practice time. And then as you run into problems, we'll be addressing them as we go through the week. All right. So number 10 says let the integral of x over 1 plus x dx, and unfortunately, they told you what let u equal on this one, and so if you're looking in your book, you've seen it already, but pretend they hadn't told you already what to let u equal. What would be your options in this problem? Because there's no inside. So what would be some potential things you could let u equal? The bottom, 1 plus x, which is what they say in the book. What else? Just x. And I bring this up because I want everybody to notice this. Don't write this down. But if I did let u equal x, what would the du be? 1 dx, which we just write dx, right? And so when I substitute, I get u over 1 plus u du. Now the whole point of substitution was turn it into some integral that was easier to do, like on page 333. What I do, I turned it into the same exact thing except using, that'd be like if I took the 5 starters out and then turned around and put them all right back in, right? I haven't really changed, I'm still in the same boat I was in before, right? Well, so the lesson from this is, don't ever, in u substitution, let u equal x, because nothing will happen. Okay, now we have another technique we're going to learn where sometimes you do let u equal x. Okay, so it's not like never, never, never let u equal x, you know, but we always got to confuse the issue a little bit, right? We got to confuse it a little bit. So never, yeah, never do it, but not never, never, yeah. So in u substitution, don't do it. Okay, don't do it. So like they told us, the only other option, real option, is to let u be the bottom. Okay, so we're going to let u equal 1 plus x. So the du is still just dx, 1 or just dx. Okay, all right. So we substitute. Now, it's pretty easy to see that the bottom's going to substitute out and be u. Equally easy to see that the dx will substitute out and be du. But if we're paying attention, if we're circling things, if whatever, it's easy to notice we've still got an x there that we have not accounted for. Any ideas? Just like we can rearrange the du equation, we can rearrange the u equation. So we can come over here and subtract 1 and solve for x. And you'll often hear me say that. You'll get stuck at some point or whatever, and I'll say, well, this is one of those where you have to solve for x. Solve for x. Okay? So we've got this extra x sitting there. So we solve for x and we get u minus 1. Now, you might be looking at that and thinking, well, that's kind of like what you just did a minute ago. That didn't really gain anything. It looks just as complicated as the other one. But it really did do something for us, very important. What? I heard a couple things, but I couldn't make it. Maybe throw it out there. What do you think? What's different about this one? Now, this does not look like page 333, right? It's not down to a simple one that we can do. But there is some algebra we can do to this that we couldn't do to this. Split it apart. What we did now, so think about this. That third idea I gave you was letting u be the bottom. Now over here it turned out to be a nice idea because we ended up with a natural log situation. Another advantage to letting u be the bottom is you turn it into a fraction with a single thing on the bottom. And we know that if you have a single denominator in a fraction, then it's easier to split apart and rewrite the fraction. So this one becomes u over u minus 1 over u, which would simplify to 1 minus 1 over u du. Notice I still put the integral sign there. This is a mistake people make because I have not done the antiderivative yet. So I still need the integral sign in the du. All I was doing some algebra to rewrite. All right, now I can do the antiderivative. What's the antiderivative of 1? Be careful. U. We're doing the antiderivative with respect to u. The antiderivative of 1 is u minus absolute value, natural log absolute value, plus c. So the u substitution didn't seem to do a whole lot, but it actually did. Now, we plug those back in, so u becomes 1 plus x minus natural log 1 plus x plus c. Now, just for the heck of it, type that back into your calculator. Yeah. Type that back in. You type that problem in, have it do the integral for you, and let's just see if we're right. Because this is what you'll do a lot of times at home when you're practicing for the gateway test. You're going to want to type them in to see if you're doing it right. What do you notice? They do not have the 1. Why? Why don't they have the 1? Think about it now. Has to do with the c. What's 1 plus some arbitrary constant? Some other arbitrary constant, right? So it would be, it's perfectly fine to leave this as your answer. I won't count that wrong. But 1 plus c is just another c. It's one bigger, so maybe we could write it a little bigger. Write a little bit. Yeah, it's d. Yeah, we'll call it d. So we'll make the c a little bigger, whatever. It's just another c. So it's absorbed, you might say, the one gets absorbed into the c. And so on your calculator, they take that into account and they don't put the 1. So if you get a situation like that and you're checking it on your calculator, you're like, wait a minute, I did that right. And it turns out you did. Okay? I don't care though, you can leave it like that. All right. One more. Number 11. Now this is actually one off of your homework here. This is, number 10 was also actually. I mean, if it's in your notes, I'm sorry, if it's in your notes, you know, that's fine. Don't need to rewrite on your homework page. But number 11 here is one of the homework problems. Now this one is a definite integral. Now I'm going to, oops, that's not x. That's a 1. The integral from -2 to 1 of x over 1 plus x to the 4th dx. Now, on number 11 and then your next homework problem you have number 13, they kind of help you a little. They don't tell you what to let u equal, but they say show that this integral would be turned into this integral by making a u substitution. So I'm going to just pretend I don't even see that right side that they give me. Same with number 13. I'm just going to treat it as a regular problem. Because think about the whole reason we're doing these antiderivatives. It's so we can use fundamental theorem part 2 to do definite integrals, really. I mean, that's why we're working on antiderivatives, so we can do definite integrals. So it makes sense that we should be able to work on some definite integrals. Well, the way you do that is you simply go through the same process we've talked about with u substitution, get the antiderivative, then put your right bracket, put your numbers in, and get your answer. Okay? Now, there's one little difference is at the end, we don't have to go back to x's. We can just stay with u's because our final answer is just a number, right? So it doesn't matter, and I'll show you what I mean by that. All right, so here we got to pick u. Now, without looking at what they did, anybody have ideas? Guys? Okay, that's a bad idea. Somebody give me another idea. It's a bad idea because it's too good of an idea and I don't want it yet. It's actually a good idea. But, be honest, many of you would not have thought of x squared. You might have thought of 1 plus x to the 4th. Would that be reasonable? Because one of the things I said is let it be the bottom. So a lot of you would have picked 1 plus x to the 4th. Now I want you to think about idea number 2 that I said, which is when you pick a u, remember you're then going to do a du. And you want that to be sitting there, somewhere in the problem. So if you let u equal 1 plus x to the 4th, the du is going to be 4x to the 3rd dx. And is there an, I don't care about the 4 because I can always move that around, but is there an x to the 3rd dx there? No, there's an x dx there. And so this is what I mean by you got to get to the point where you can see a few steps ahead. Okay? And that's what I would be looking at. If I thought to make u equal 1 plus x to the 4th, I would think, but then I'll do du, and that'll be x cubed, and I don't have an x cubed, so that's a bad idea. Okay, but that's because I've done enough of these where I let u equal 1 plus x to the 4th, ran into a dead end, had to start over. That's what's going to happen to you. So we will take Alex's idea, and 2 good things are going to happen. First one, the one we just talked about, is when I do the du, I'm going to get 2x dx. And I know the 2 I can just move around, but the x dx is good because I can see an x dx setting right there. That's the first good thing. The second good thing is what's going to happen on the bottom. What am I going to get on the bottom? 1 plus u squared, and what's 1 plus u squared on the bottom? Arctangent. See? So those are the things that I would be seeing and thinking of as I'm trying to decide what to pick for u. All right. So we start looking at this and we start subbing out. We see this 2's kind of in the way here, so I'll move it to the other side. It becomes a 1/2. So I got one, okay, I got that. So now I'm going to circle this. I got my x dx. That x dx is the same as 1/2 du. I see what I'm left with down here, which is a 1 over 1 plus u squared. Right, that x squared gives me that. Very easy now that this is arctangent. Now, however, and I've gotten ahead of myself here a little bit. First of all, I don't need a plus c because this is a definite integral. And we don't need the plus c because when we subtract it, the plus c's will subtract out. Second thing is, what didn't I circle over here? The -2 and the 1. I got to substitute those out too, because aren't those x's? Think about your area. You're talking about the area from -2 to 1. Those are x values. -2 and 1 are x's. They got to come out. I can't put those in here with u's. I can't mix x's with u's. So I need to sub out the -2 and the 1. Those are x's. How can I turn them into u's? This line right here. That's how I can turn x's into u's. I can put a -2 right in here for x, and it turns into 4. I can put this 1 right in here for x, and it turns into 1. So when I'm doing a definite integral, I not only have to sub out the x's, I have to sub out the x coordinates, my endpoints, and turn them into u's, and I do it by my u equation right there. Now we can do our right bracket. Now we don't have to go back to x's. We can do our right bracket, 4 to 1, and now we can just write 1/2 arctan 1 minus 1/2 arctan 4. And now that's good enough. Now we'll get into what trig ones you need to know. Actually, arctan 1 is pi fourths, I believe. So probably should simplify that. Arctan 4 is not one we would know. Okay? So you're able to simplify a little bit. Okay? But for right now, we'll just leave it there. Okay? And we'll talk about whether on the gateway test it'll be necessary to do that or not.
So would you not have to, like, you have it as 1/2 arctan of u, would you not have to change it into 1/2 arctan of x squared?
That's right. That's right. That's the point. Because think about it. A definite integral is just a number. So it doesn't matter if you're u's or x's. In the end, you just have number as your answer. Now, I will say that it would have been acceptable, and I don't think it's any shorter or any longer, but it might be more consistent. If you want to be in the habit of always going and changing them back to x's, you could take that extra step to turn this into 1/2 arctan x squared, but then what would be on your right bracket? The -2 and the 1. And when you put them in, since you have x squared that you're plugging them into, you'll still end up with the same answer. Right? Because you'll put -2 into x squared, you get 4, and you'll put 1 in, and you'll get 1, and it'll be, you see what I'm saying?
Yeah.
If you'd rather do that because it's more consistent, that's fine. But here's what I would caution you. You'd be kind of like those Algebra 1 kids who always want to get the x on the left side. Right? I don't want to learn anything new that confused me. I just want to always get on the left on the other side. Well, what happened is you might run into some issues if you don't understand the other thing. One of those issues you might run into is on the final, in the multiple choice question. Sometimes they ask them like this, where they don't ask you for the final answer, but they ask you what would be these coordinates. You know, what would be these two numbers here when you do the u substitution. So you have to at least know about changing these x's into u's, how that works. Because you may run into questions that deal with that. But to find the final answer here, we could have went back to x's and used the -2 and the 1. All right? Okay, here's your homework on that assignment sheet. Okay, and you can have the last 25 minutes here to work on this. Oops, sorry everybody watching at home, that's supposed to be a 1 inside there. There you go. Okay. Right below the quiz, right below quiz 5153 on that assignment sheet, okay, there's a group of 3 lines all together. Now the first line we already did, 1 through 9 on. Okay? You're going to do the second line and the third line, the one in bold. Now the second line, we already done 10 and 11. Okay? So you do the rest of that third line, that second line there, 10, 11, 13, 22, and so forth. So you do that line. And then the bold line, it says do sum of 23 through 73. Let's do 10 at least. So you pick any 10